today we are going to talk about the satellite-based remote sensing. First of all, we are not talking about some other band, some other wavelengths. We are only talking about optical remote sensing, with a special attention to the application in the atmospheric environment. That always means the AOD, the aerosol optical depths. There are some other satellites designed for NOx and SOx or ozone. I won't talk too much about them, but I'm going today and next Wednesday, I'm going to concentrate on the MODIS. After this lecture, you're going to know the definition of remote sensing, the element of remote sensing system, that means the hardware, the data product of remote sensing system, that's the software. The result of software, you don't need to know the detail about the software. And you can talk about the application of remote sensing in the atmospheric environmental research. Okay, and I hope you can answer this question. What's remote sensing? But not the naive version, the sensing remotely. You need to know the definition of it. Why are we trying to locate the sensor away from us? Because satellite, we need to invest billions of dollars to lift the sensor to hundreds of miles away from us. Why are we doing that? Why don't we put them as close as possible? At what cost? How much? You don't need to know the exact cost. You just need to know the general idea. And what are the two types of orbits based on altitude? What are the four resolutions of remote sensing image? What does AOD means? What's the difference between satellite-based AOD and PM2.5 VLOD? Okay, let's start from the definition. Remote sensing is the science and the art of obtaining information about an object, area, or phenomenon through an analysis of data required by a device that is not in direct contact with the area, object, or phenomenon under investigation. The most important part of this definition is not in direct contact. As I said, we are trying to leave the sensor as away from us. Normally, if you really want to know the detail of something, we are trying to look closer, right? Just like what I'm doing. I'm trying to look at your face. But now I'm trying to move away from the camera. Why am I doing that? Because if I move away from the camera, I can see all of you. Otherwise, I can only see one of you. If I can see all of you, I can scan all of you, and I can use a computer algorithm to scan all of you. It's much faster. If you think it as COVID-19 surveillance, if you can put a camera on the top of a subway station, you can measure the temperature of thousands of people. That's of very high importance. Sometimes, if you want to measure something with some direct contact with something, sometimes it's invasive and aggressive. You can't ask everyone to take off their shirt to measure their temperature. You can't put the thermostat in their mouth because, due to the sanitary condition. And even though for a single picture it's much more expensive, but on average it's much cheaper. If you have a sensor maybe 100 kilometers on the top of the surface, it always means you can measure something unreachable for normal field trip. Just like in the middle of the Arctic area, you can use satellite remote sensing to see a polar bear that. But if you want to use a field trip, it can also cost millions of dollars. It also has some area-specific advantage. For example, if you want to know the harvest of crop in North Korea, it's impossible, right? But if you have a satellite, you can know that very easily. All of this has a cost. That's the accuracy. If you're not looking closer enough, you are losing a lot of accuracy. But you need to find a balance between these benefits and the loss of accuracy. Distance matters. There are 4 pictures, all of them about the Earth, but they are taken at different distance. From the left to right, it's getting farther and farther away from the Earth. The left one, the ISS, means the International Spatial Station. The orbit is pretty low, actually. It's only 250 miles away from the Earth. That means you can see the curve on the horizon, right? That means it's not very far away from the Earth. It cannot look a big area at the same time. And let's move right. It's a GOES-R. GOES-R means the Geostationary Observational Environmental System. That's a geostationary orbit, geostationary satellite. The distance from this platform to the ground surface is 22,000 miles. It can have a single scan of the whole of half of the Earth at the same time. You can see it has some details, but you can't have a huge camera on this platform. That means the spatial resolution cannot be pretty high. The spatial resolution of GOES-R is only 3 kilometers. At such spatial resolution, you can't get a lot of details. But for the International Space Station, you can see the scale of the city. You can only detect the road network. You can have a lot of information. That's a loss of accuracy for the high efficiency. But if we move further away from the Earth, let's say, Moon is also a satellite, but it's a natural satellite, right? If we take a picture, if we look back from Moon, you can see that's Earth. It's a small blue dot. You can't tell any details on the Moon, even though it's a satellite. I promise nobody is going to send a satellite at such latitude because it doesn't make any sense. But for some other purpose, if we go further away, the Voyager 1, I think that picture was taken maybe 3 years ago, 4 years ago. At that time, it's 4 billion miles away from Earth. You can almost, I have a strong sunlight in the living room. I can't see the Earth, but maybe some of you can see that. It's just a single pixel. So that means that the comparison between these 4 pictures means that you can't go too far away from Earth. You need to find a balance, but you can't. It's up to the usage of the satellite. Okay, some history about satellite.